heat transfer mechanisms. What we have done up to this moment was to look energy by itself, right? How energy balances, whether it's coming in, out, generated, or how it results in it being stored, how temperature increases, or how phase changes happen and what their implications are. All this we have seen, right? And I mentioned that it's a little bit like your bank account, in which you have to know the money that comes in, the money that you spend, some money is generated as interest, and that is going to be your bank account balance. But that is kind of a Swiss bank account. We never ask where the money comes from. We didn't ask if the money comes from your good, honest work, or you were dealing things on the street, right? We didn't ask any of that. But now, that's exactly what we're gonna do, like to find out what form the heat is exchanged, right? Like, what is the mechanism with which it comes in or out? We're gonna do that analysis twice in this course. The first time, we're gonna do it this week, in which we're gonna look at the heat transfer mechanisms only from their, what is called the phenomenological expression. We're gonna write a formula that helps us calculate it, right? And different heat transfer mechanisms are gonna have different formulas. Later on, we're gonna spend the whole second half of the course just seeing, okay, the coefficients we used in these formulas, where do they come from? This week, we're going to put the whole complexity of fluid flow and heat transfer coupled into a single heat transfer coefficient H, right? So it's very powerful because we can do many things. At the same time, it's quite simplified because the problem is much more complex. But what is incredible is that all that complexity ends up typically being in similar values. And that's where we're gonna start with these general similarities that give us a big power of prediction. And later on, we're gonna move into like getting into the details about where these similarities come from. Okay. All right, these are the notes that are uploaded about heat transfer mechanisms. And of course, we're gonna talk about some things that you might have heard these words already, right? You already heard the words such as convection or radiation or conduction. Probably you haven't heard much about contact resistance, but you're gonna see how we can smuggle it into all the other ones you already know, and has a very similar formula and helps you think of new and important problems. So, let's see, let's get this. Let's start talking about heat rates and heat fluxes. So far we had big Q, that meant how many joules had been exchanged. Then we said, okay, if we want to know how many joules per unit time, that's our small q, that is watts, right? It is for energy rates. Now I'm going to talk about heat per unit time, that is a small q, but also per unit area, right? And that is when something is per unit area. In this class, we use the notation double prime, right? One prime would be per unit length, and you're gonna see later that per unit volume, we use triple prime. So Q double prime, Q double prime here is the small amount energy that is exchanged in a small amount of area. what is this area? Okay, in things like convection or radiation, the heat is exchanged through a surface. So this will be a surface area. And for that, we tend to use this notation of A sub S, meaning it's a surface area. Other mechanisms, such as conduction, the conduction happens inside the body. And in that case, the area that matters is the cross-sectional area. And because it's in conduction, we use this A sub C, that is the area through which the heat is flowing inside the body. Many of the problems we do in this class, we have that the heat flux is uniform over the surface we care about. So this differential can be turned into just like the small q, the amount of watts, is proportional to the heat flux multiplied by the area that matters, whether it's surface areas or cross-sectional area, right? Okay, good. So now we know big Q, we know small q, we know small q double prime. Each of those are important concepts that have clear meanings. Let's start with the first heat transfer mechanism, which is the most difficult of all when we look at them in detail, but it's the simplest of all when we just capture it with math. And who knew that math makes our life simpler instead of more difficult? But this is the case. So let's see. Okay, let's say we have a surface that is this one over here. And this surface is at a temperature that we're going to call Ts. That is following the same notation of the book. Ts is for temperature at the surface. Over this surface, we have a fluid. The fluid can be water, fluid can be air. The fluid can be molten tin in a nuclear reactor, right? It can be anything as long as it is a fluid. And this fluid has a temperature we're going to call T infinity, which is the temperature of the fluid far away from the surface, right? So this is the case of a fluid going inside a pipe. This is a case of a fluid going over a fin in a fin cooling. And the amazing thing is an equation you might have seen in introductory physics, is for all the complexity of convection that you're going to see later, this mixture of advection and conduction together. But in the end, the amount of heat, the heat flux that is exchanged by convection is given by this formula number 3, this equation number 3 that you have on the screen right now. And is the heat flux due to convection is proportional to the difference between the surface temperature and the temperature of the fluid far from the surface. And the coefficient of proportionality is the convection coefficient, H. And H is the reason why we call enthalpy I in this class. So how much heat am I losing through a surface by convection is this convection coefficient H multiplied by the temperature difference between the surface and the fluid far from the surface. Look, now this is kind of amazing because we have a formula that is ridiculously simple. All the complexity of advection and conduction and turbulence and buoyancy and material properties, crazy stuff, all goes inside H. Now, to some extent, I would have said nothing because you can always say, hey, everything I don't know, I give it a name. But the amazing thing is that H has values that are quite uniform under similar circumstances. For example, if we look at convection coefficient of gases, we have, or liquids, we have two types of convection. One that I explained in the notes. One is called the natural convection. That is convection that happens because the fluid is moving due to buoyancy forces. For example, when the air that is moving on top of a bonfire, right, that makes you see things blurry, that air is going up, but nobody's forcing it to go up. It's just that that air is hot and wants to move up. So if you're at home now and you put your hand just like me, your hand is at 37 degrees, give or take. Your room is at 20 degrees, give or take. And the hotter hand is hitting the air around it, and you don't see it, but that air is moving up and nobody's forcing it. That motion of air causes advection, and together with conduction, that creates convection. And because there was nobody forcing it, that is called natural convection. Now, we understand that. What if there is wind, right? If instead of being inside the room, I was outside and it was windy, now the wind typically makes things feel colder, right? And it's because the heat exchange increases, because we have a forced velocity imposed on the fluid, not just buoyancy, but it's forced from outside, right? We have a different problem. So if we go back now to our notes, a typical value for convection coefficient for natural convection is more or less 10 watts per meter square Kelvin. We're going to learn how to calculate it properly, but I'm giving you a ballpark value, very ballpark. But so this is quite awesome. As you are sitting in front of your computer, you are losing heat. That is more or less your 37 degrees minus the 20 degrees of the air times this convection coefficient, that is 10. We're going to have an example with that. If it is windy, if it is a force velocity, and I'm not even saying what velocity is force, right? Like this is typical values. The convection coefficient is kind of 10 times higher. That's why you feel cold when there is wind, because all of a sudden the convection coefficient is 10 times higher and you're losing 10 times more heat. Interesting enough, if it is, we talk about liquids, we have factors of 1 order of magnitude change too. This is very ballpark. But if you were to do the same experiment I mentioned in water, and you put your hand at 37 degrees in still water at 20 degrees, you're going to have natural convection, and it's going to be of the order of 100 watts per meter square Kelvin. Interesting. Just because it's a liquid, is 10 times stronger. Now, if you're swimming in water, your very fast swimming velocity is going to be forcing this flow of water over your body, and your convection coefficient is going to be of the order of 1,000 watts per meter square Kelvin. Let me tell you something, an amazing thing of this moment. You would be a happy person sitting in a room at 20 degrees. You will not be at all a happy person swimming in water at 20 degrees. And now you know why. You would say the water is cold, but the water is at the same temperature of the air. So we're missing something, right? The water is cold, but it's the same temperature of this room, and I don't say it's cold. What happens is, as I'm sitting in this room at and losing heat at 10 watts per meter square Kelvin, My metabolism is perfectly balanced with that. Happy person. If I were to take a dive now and start swimming in water at 20 degrees, I would be losing 100 times that amount of heat, way much more than my metabolic heat. I'm gonna get cold very quickly, right? Very interesting. That's what explains why we want our water hotter than our air to feel comfortable. Not everybody knows that. Everybody knows what you want, what they want, but they don't know why. Now you do. So let's do an example of calculation of heat loss by convection. This is just to go through the mechanics because this problem is so simple that it's like Mickey Mouse, right? So the question here is, if we have a surface of 1 meter square at 40 degrees C, and we cool it by natural convection in air at 20 degrees C, right? That would be the case of having a 1 meter square surface at 40 degrees in this room or the room where you are now. The question is, what is the total heat loss? What is the total heat loss by the surface? And okay, let's assume that this Q double prime is constant over the surface. So we can multiply Q double prime by the whole area. Okay, the solution says, what is the heat loss by convection? Then is area, in this case, is the surface area of this surface times the Q double prime. And Q double prime is H times the delta T, delta between temperature of the surface and temperature of the fluid. Just it said natural convection for now, and I'll give you a value, or you will assume a typical value. In this case, I gave you no value for convection, but I said natural convection, and I said in air. So typical value, 10 watts per meter square Kelvin. Is it exact? No, it's not exact. Is it practical? It's amazingly practical. And now plug and chug. We put the area 1 meter square, we put this 10 watts per meter square Kelvin that I just mentioned to you, the delta temperature, and it says 200 watts. That's quite a bit, right? That's quite a bit. You would need to put 200 watts to keep this plate in thermal balance if you want to. You might also wonder why we didn't do a control volume and why we didn't write an energy balance in this case. And we didn't because we were not asked to. In this case, it says, given this heat transfer mechanism, what is the rate, right? And here I have it. Something I forgot to mention here in this equation number 3. If we talk about Q convection always in positive terms, whether you gain energy, whether you gain 100 watts or you lose 100 watts, the Q by convection is 100 watts. The difference is going to be if it is a Q in by convection or it's a Q out by convection, right? So if you're gaining heat by convection because you put your hand in an oven, so that would be the 100 watts in the Q in. If you're losing the heat by convection because you stuck out your hand out of your window and it's below 0, then those same 100 watts would go in the Q out. Good. I think this is quite simple, and I think the notes are reasonable too. But if anybody has a question that would help me clarify for the whole class, you can tell me now. And of course, if not, we can discuss in the office hours later. The incredible complexity of convection has been captured in this single parameter H, and we already made a calculation. Let me tell you about radiation now. Radiation is interesting. Radiation has a more complex formula, but it has a similar spirit. And this gets into quantum physics, the origins of this. And we don't need to know quantum physics because we're engineers, but we know how to reduce it to a formula that is practical. And it says that the rate the flux, the heat flux exchanged by radiation has this formula in which we have epsilon sigma Ts to the 4, T cert to the 4. Let's go through what each of these things mean. Ts is surface temperature, as you know. In radiation, we must use absolute temperature. We cannot use like degrees C. These are always kelvins. Now, T cert is the temperature of the surroundings. Please take a quick look at the notes to see what the difference between temperature of the surroundings and T infinity is. Sometimes it is the same, sometimes it's not. But to give you an idea, if my body is at 37 degrees, the walls around me in this room, you don't see, but these walls are at more or less 20 degrees C. So this temperature of surroundings would be 293 Kelvin. And if the air inside this room was at a different temperature, but the walls are still at 20 degrees, what matters is the surrounding temperature, the walls, right? So even if the air was 100 degrees, if the walls are at 20, for radiation, what matters is the 20 of the walls. So this is T surroundings. Sigma is the Stefan Boltzmann constant. That is a fundamental constant of physics that is tabulated. So this is never going to change. And epsilon is the emissivity. So epsilon is to some extent somewhat similar to the convection coefficient. The emissivity of a surface, we're going to see later, depends on many things. Depends on the wavelength, depends on the orientation, depends on a bunch of things. But we are going to say, you know what? All those things all together for a given surface, I assign a value of emissivity. Emissivity can never be higher than 1. That would be a black body, right? Something in which emits the maximum possible amount of radiation. Normal surfaces emit less than 1. And we discuss here in the notes, but most dull materials, including skin, is more or less 0.9, give or take. Again, this is very approximate. And most shiny things, like a shiny metal, those have a low emissivity, like 0.2, right? And of course, there are books on tabulating these efficiencies and ways of calculating them and many considerations. But for now, you get this sense. So how would you make a calculation of heat loss by radiation? So let's look at an example, the same as before, but now from the point of view of radiation. So, something I would like to clarify. Radiation is exchanged between two surfaces. Radiation, the way we're going to see it in this class, is not a volumetric property. Between these two surfaces, you have to have a path for the radiation to travel. So if you have vacuum, you're fine. But maybe you don't have vacuum, maybe you have air, right? So, or maybe you have other things in between. When the radiation can get through, we call that a transparent medium. And we're gonna assume until the last week of class, we're gonna assume that when something is transparent, it's 100% transparent. Some things are not transparent, and we're gonna call them opaque. And until the last week of class, when we say something is opaque, it's 100% opaque. Let me give you examples. Air is transparent to radiation, and we're gonna say it's 100% transparent to radiation. Most radiation is infrared. Water, you might be inclined to think that water is transparent because your eyes tell you it's transparent. However, your eyes work in the visible wavelength, but most radiation is infrared, and water is opaque to infrared. Same with glass. The glass is good for visible wavelength radiation that is of the order of just shy of a micron. But for thermal radiation that is infrared, that is longer than a micron, glass is opaque, right? So air and most gases, we're going to assume that radiation gets through. Water, glass, wood, steel, all those are opaque and do not convey radiation through them. They can emit, but they cannot convey. So in this example, we talk about a glass surface of 1 square meter is at 40 degrees C. For example, a window, and is surrounded by an environment at 20 degrees C, right? Calculate the heat loss by radiation. And let's assume an emissivity of 0.9 for the glass, right? A glass is not a shiny metal, right? Metals have these special properties. Their shiny color, their color already is a giveaway. So although we can see through glass, for the most part, we can assume it's like quite an opaque and emissive material from the point of view of radiation. So same thing as before. Heat of radiation is assuming that the radiation is uniform over the surface, is surface area times the heat flux. And we have the heat flux is given by the radiation law, that is epsilon sigma T surface to the 4 minus T surroundings to the 4. And the Stefan Boltzmann constant is 5.67 times 10 to the minus 8 watt per meter square Kelvin to the 4th. And we calculate it, right? And what do we see? We see that that in this case, the amount of heat loss by radiation is not all that, is 100 watts, right? Before it was 200 something, right? We had 200 watts for the heat loss by convection under natural convection. And in this case, we have 100 watts. So for opaque surfaces near room temperature, the heat exchange of radiation is comparable with the heat exchange by natural convection. Let me tell you something cool. Most of you must be familiar with thermoses, and I hope not all of you have broken thermoses, but I have. And you get to see that inside they have like this double wall, and this double wall is shiny, it's like chrome plated, right? And the reason is that in this double wall, sometimes they pull a vacuum, which is a good thing, and sometimes they don't. But in either case, they would have either no convection, because in vacuum there is no fluid to move, or it would be radiation heat transfer. And by having them chrome plated, this chrome color, this finish, they would move from an emissivity of about 0.9 to an emissivity of about 0.2. And the heat exchange by radiation would be much smaller. In the case of vacuum, that is what dominates. And in the case of not having a vacuum, but having a little bit of natural convection, we would be reducing the whole effect kind of by half, because we said radiation is more or less comparable to natural convection, and we would be taking radiation away. So that's pretty cool. I think this is a good point to stop. And we're gonna wrap up with radiation, talk about contact resistance, and also conduction later on Wednesday. Thank you, everybody. I'm gonna stop here, and we're gonna have office hours starting in a couple minutes. Thank you.